In this part of the video, I'm going to go into detail about what a researcher needs to do before reaching a cause and effect conclusion or inference in a psychology experiment. But before I go into any detail, I want to share an example with you that this video will be based around. I want you to imagine that one of your classmates has done the psychology experiment that I described in the last part of this video. I want you to imagine that your classmate has done an experiment to test the effect of temperature on memory, and your classmate has put one group of people in a 60-degree room and one group of people in an 80-degree room, and your classmate has given both groups of people the same recall test, and your classmate has collected a recall score from each participant. And I want you to imagine that your classmate shares this bar graph with you just to share his or her results with you. And in the bar graph, you can see that the mean recall score of the cold group is 7.4. You can see that the mean recall score of the hot group is 5.7. So the cold group did do better than the hot group by about 2 points on average. What I want you to think about is, if all you have is just this bar graph, what can you conclude about the effect that temperature had on memory in the experiment? Well, you might be tempted to think that this bar graph is showing clear, convincing evidence that temperature had an effect on memory. After all, the cold group did do quite a bit better, and the hot group did do quite a bit worse. But if all you have is just this bar graph, then all you really know is that something about the cold group caused them to do better, and something about the hot group caused them to do worse. In other words, all you know at this point is that some difference between these two groups of people caused one group to outperform the other. And that difference might be temperature, but it might be something else. It might be that the hot group was a little bit more tired that day, or it might be that the hot group had more people that are just good at memorization in general. So at this point, you can't conclude anything without more information. And the point of this video will be for me to explain why this bar graph alone isn't enough to reach a cause and effect conclusion, like a conclusion that temperature had an effect on memory. So before you can reach a cause and effect conclusion confidently in an experiment, you have to eliminate, or at least confidently eliminate, three possibilities. And I'm going to go through each possibility one at a time, and each time I'm going to talk about what a researcher needs to do to eliminate, or at least confidently eliminate, that possibility. And what we're going to be going through is a process of elimination. We're going to talk about how a researcher eliminates three competing possibilities so that hopefully the only possibility that's left is the researcher's hypothesis. And hopefully the researcher can say that the hypothesis is supported at that point. So it's going to be kind of like how a student eliminates possible choices on an exam question. You might have been in a situation before where you're stuck on a multiple choice exam question, and let's say you're able to confidently eliminate three of the four choices. Well, at that point, you would be confident that the fourth choice is correct, because that's the only remaining choice. That's pretty much how this is going to work. So the first possibility that needs to be eliminated before reaching a cause and effect conclusion is a possibility that the results are due to a pre-existing difference between the groups in the experiment. And when I say a pre-existing difference, I'm meaning a difference that existed before the experiment began. So I'll share a few examples of possible pre-existing differences, just so you get the idea down. Let's imagine for a moment that in your classmates' experiment, the cold group is a classroom of fifth grade students, and the hot group is a classroom of senior psychology majors. If that's the case, then there are definitely some pre-existing differences between these two groups of people. First of all, the fifth grade class is quite a bit younger than the senior psychology class. So the two groups are different in age, and that's a pre-existing difference because that difference in age existed before this experiment began. The two classes were already different in age before they were brought into this experiment. And, another pre-existing difference between those two groups of people would be a difference in height. The fifth grade class is obviously quite a bit shorter on average than the senior psychology class, and that difference in height existed before the experiment began, so it's a pre-existing difference. The two classes are also different in years of education. The fifth grade class has a lot less education than the senior psychology class, and since that difference existed before the experiment began, that's a pre-existing difference. So, like I said, any difference that existed between the groups of people before the experiment began is a pre-existing difference. And this first possibility is eliminated if the participants were randomly assigned to groups. So if your classmate randomly assigned the participants to the hot room and the cold room, then this first possibility is eliminated. We would know for sure that the results are not due to a pre-existing difference between the hot group and the cold group. And that's because if the participants were randomly assigned to the two groups, then the two groups didn't even exist before the experiment began, and there can't be any pre-existing differences. If the researcher created the two groups during the experiment through random assignment, then there can't be any pre-existing differences. Like I said, the groups didn't even exist for the experiment. So when participants are randomly assigned to groups, three things are true, and I'll go through them one at a time. First of all, when participants are randomly assigned to groups, there's no bias in the way participants are being assigned to groups. Random assignment is bias-free. Bias is anything that pushes the results in a certain direction. So I'll share maybe one or two examples of bias. Let's imagine for a moment that your classmate put a group of fifth grade students in the hot room and put a group of senior psychology majors into the cold room. If your classmate did that on purpose, that would be bias because that's going to push the results in a certain direction. The cold group is going to do better simply because of being adults, and the hot group is going to do worse simply because of being younger children. So that would be biased. But when you have random assignment, there's no bias. The results aren't being pushed in a certain direction. Also, when participants are randomly assigned, all differences between the groups are due to chance. So when participants are randomly assigned to groups, the two groups aren't perfectly equal in every way. For example, one group might have a few more females just by chance, and one group might have a few more males just by chance, but that would be a chance difference between the groups. Also, when participants are randomly assigned to groups, the groups that are created tend to be roughly similar to each other. And I need to explain what I mean by roughly similar. When I say that the groups tend to be roughly similar, I don't mean that the individual participants tend to be roughly similar to each other. What I mean is that the groups tend to be roughly similar to each other. Group 1 as a whole tends to be roughly similar to Group 2 as a whole. The makeup of Group 1 tends to be roughly similar to the makeup of Group 2, and that's especially likely if there's a large number of participants. And if you think about it, I think this makes sense. Let's imagine that I take 100 people and I randomly assign them to two groups of 50. It's not likely that the first group will be entirely shorter male introverts and the second group will be entirely taller female extroverts. The groups aren't likely to be that widely different just by chance. It's more likely that the first group will have some males and some females, some introverts and some extroverts, and some taller people and some shorter people. And the second group will also have some males and some females, some taller people and some shorter people, and some introverts and some extroverts. In other words, it's likely that the makeup of group 1 will be roughly the same as the makeup of group 2. And I want to quickly explain why the sample size matters. If I took, let's say, 4 people and randomly assigned them to two groups of 2, I would be much less confident that the two groups will be roughly similar to each other because random assignment is less reliable with a small sample size. If my 4 participants include 2 males and 2 females, I could easily send 2 males to one group and 2 females to the other group, just by chance. Or if my 4 participants include 2 tired people, I could easily send those 2 tired people to one group and send the 2 alert people to the other group, simply by chance. Like I said, smaller samples are less reliable. So the groups are more likely to be similar to each other when a large number of people are randomly assigned. And I want to explain why random assignment is important and why it's important for these groups to be roughly similar to each other. As a researcher, you want the groups to be roughly similar to each other so that the groups can be fairly compared. If I'm doing this experiment over here, and the cold group is a group of fifth grade students, and the hot group is a group of college students, I can't fairly compare those two groups to reach a conclusion about the effect of temperature because the college students are almost guaranteed to outperform the fifth grade students, and um, that's likely to happen regardless of which group is in the hot room and which group is in the cold room. So the two groups simply can't be compared fairly. But if I take a large enough number of participants and I randomly assign them to two groups, um, then those two groups can be fairly compared because they're probably roughly similar. And if the cold group does outperform the hot group, I'll be much more confident that the temperature is what caused that difference in performance. So yeah, that's why random assignment is important. So if you're still having a little bit of difficulty understanding why it's important for the two groups to be roughly similar to each other, it might help to imagine an experiment with only two participants, and one person is in the cold room and one person is in the hot room. In that experiment, you would definitely want the two people to be similar to each other. You wouldn't want the cold room to have a college student and the hot room to have a 10-year-old child because you can't fairly compare the two people to reach a conclusion about the effect of temperature. So, just like how you would want those two people to be similar to each other, you would want um, two groups of people to be similar to each other if you're comparing a cold group and a hot group. So yeah, that's it for this video. In the next part of the video, we'll move on to possibility number 2.